liquids flow. Gases are sort of like liquids in that both change their shape to fit their container. However, liquids are what we say incompressible. This is because their molecules are fairly close together, and it's hard to push these molecules on top of each other. Whereas a gas, it has molecules that are very far apart, thus making it compressible, as shown. When talking about liquids, it's important to talk about density. Say we have a block of copper, and I make it smaller and smaller and smaller. There should be an inherent property that makes copper copper. That is density, given by rho, which is mass over volume. The standard unit is kilogram per meter cubed. Water has a density of 1,000 kilogram per meter cubed, and mercury has a density of 1,300. No matter how small I make my copper block, density is independent of size. An important topic when talking about liquids is pressure, given by P. That's just a P, like LMNO-P. It's given by force divided by area because all liquids inside their container exert a force perpendicular to their container, which is why the fluid shoots out of the sides when you punch a hole in it. Part of that pressure comes from the atmosphere above the container. What is our atmosphere? Well, it's the air above the surface of the Earth. Our atmosphere extends about 30 kilometers above the surface. So when you are standing at sea level, you've got a 30-kilometer air column on top of you. Now, this air column has weight, and that weight, we say, is 1 atmosphere, which is 101.3 kilopascals. 1 Pascal is 1 Newton per meter squared. Now back to our container with the 3 holes in it. The lower the hole, the faster the water is going to come out. This is because there is a greater pressure with greater depth. Now, we all know this from diving into a pool, and then we feel like our ears are going to cave in the lower we go. The greater the depth, the greater the pressure, because there's more weight above you because there's more water above you. Pressure is very important because it allows our circulatory system to function. Pascal's principle says if you increase pressure in one area, pressure increases everywhere else. When your heart constricts, the pressure increases and allows the blood to flow through the rest of your arteries. The last subject we're going to talk about is buoyancy. Buoyancy explains why a life preserver floats, or someone that made a mob boss angry swim with the fishes with a pair of concrete boots. Say I have a liquid at rest in a container. We would say this liquid is hydrostatic, and I plot out a certain volume of that liquid. It has a net force of 0. It has its weight directed down and a buoyant force directed up. These two are equal but opposite. Now, I fill in that exact volume with an object. It also experiences a buoyant force that is equal to the buoyant force of the water. In other words, the buoyant force of an object equals the weight of the displaced water. Legend has it, ancient Greek mathematician Archimedes came up with this principle when he stepped into a very full bathtub. The water displaced and he shouted, "Eureka!" and he ran up the streets naked. Archimedes more than likely used this information to help out his king. His king had a very nice crown and might have been made out of gold, and he wanted to be certain. Gold has a certain density, but density is mass over volume. The volume of the crown would be very difficult to calculate given its shape. So Archimedes had this idea. He submerged the crown in a fluid of known density. Here we're going to use water for our example. Our crown has a mass of about 0.845 kilos. The tension in the string is also measured, about 7.81. The weight of the crown out of liquid is around 8.3 newtons. Now, if we draw a free body diagram, we have the weight of the crown, the tension force, and the buoyant force. The sum of our forces equals 0. So that would be tension plus buoyant force minus weight equals 0. Solving for the buoyant force, we get weight minus tension. Both of those things are known, so we can calculate the buoyant force. We know buoyant force is equal to the weight of the water displaced. Now, the volume of the water displaced is equal to the volume of the crown. So the mass of the crown is equal to density of the crown times the volume of the crown. We solve for the volume of the crown. Plug that back into the equation because we know that the volume of the crown equals the volume of water. So we have mass of the crown over density of the crown. And eureka! We can solve for the density of the crown because everything else is known. Now, working this out, you get a density of around 17,000 kilogram per meter cubed, which is not gold. This might have made a very happy Archimedes, but a very unhappy blacksmith.